It's funny what questions you don't think to ask. You hear something and you accept it without objection, and then later, sometimes much later, you stop and go, wait a minute. This happened to me because of a topic most of us don't ponder much: neutron stars. It's not like I sit around thinking, hey, how about those neutron stars anyway? I may be a nerd, but I'm not that big a nerd. In any case, I was thinking about it because of some research that I'd read that I'll tell you about in a little bit. I first learned about these peculiar objects because I took a class in astronomy at the University of Louisiana. The teacher, Dr. Whitmire, explained it as follows. During most of a star's life, it exists in a balance between two forces: the outward push created by the heat from the star's core and the inward pull created by the gravity of its mass. If those two are in balance, the star is stable. But towards the end of a star's life, its core exhausts its fuel, so that outward push from the heat decreases and the star starts to collapse. With small stars, like our Sun, the collapse continues until the mutual electric repulsion of the atoms that make it up is sufficient to halt the collapse. Stars like this are called white dwarfs. In larger stars, though, say 10 to 25 times the mass of the Sun, that mutual electric repulsion isn't enough to stop the collapse. The star continues to shrink until it's about 10 kilometers across. That's the diameter of a small city. This creates some pretty unusual conditions. For one thing, it's unimaginably dense. The estimate is that a teaspoonful of neutron star matter would weigh as much as a mountain. The other thing is its surface is the smoothest surface known. The gravitational pull is so huge that it just crushes out all the irregularities. Although it bears mention that the Earth is a lot smoother for its size than you think. We look around us at all those hills and valleys and mountains and so on and think it's pretty rough. It turns out the topographic relief on the Earth is less than the topographic relief of a scratch on a billiard ball. The salient point here is that the collapse of a neutron star is so intense that it actually crushes the electrons into the nucleus, and you end up with a large ball of neutral particles. Essentially, a giant atomic nucleus. So far, so good. But the next thing Dr. Whitmire told us is the thing that should have pulled me up short and made red flags wave, and didn't. He said that neutron stars have huge magnetic fields, and not only that, they're spinning incredibly fast. The reason is because of the conservation of angular momentum. It's just like when a figure skater pulls in her arms as she's doing a spin and her rotation rate increases. Here, though, the rotation rate increases almost to a point where you can't imagine it. Neutron stars rotate at 30 times per second, and a point on its surface is estimated to travel at about 1/3 of the speed of light. That rotation rate, coupled with the enormous magnetic field, creates magnetic funnels that jet electromagnetic radiation out, making a neutron star basically like a giant lighthouse. Neutron stars that do this seem to flash on and off. They're called pulsars. This is the point where I should have realized that something odd was happening, especially since I had just taken a course called electromagnetism. In this course, we learned that James Clerk Maxwell figured out that the way that you can create a magnetic field is to have electrically charged particles moving. And remember, the interior of a neutron star is electrically neutral. So what could create an enormous magnetic field in a neutral object? And it really is enormous. They estimate its strength at about 10 million teslas. By comparison, the largest magnetic field ever artificially created on the Earth was about 16 teslas, and it still was strong enough to levitate a frog. I'm not making that up. The reason is not satisfactorily explained yet. One possibility is that even though the neutron star is neutral as a whole, it still has some charge separation, and so when it whirls around, the charges actually create a magnetic field. Another possibility is that because neutrons are made of 3 quarks, and quarks themselves have a charge, that their magnetic moments might line up when the star spins and create a magnetic field that's sufficient enough to generate the odd behavior of a pulsar. So neutron stars aren't the simple things we thought they were. That shouldn't be a surprise. It seems like every time we answer one question, 3 more crop up. But the reason this came up was because of some research that shows that they're even odder than we thought. There's a neutron star that was recently discovered called J0030 plus 0451, euphonious name. It's a pulsar. It has those jets coming out of it that seem to flash on and off. But what's odd is that most pulsars we've ever studied have the jets aligned with the spin axis of the star, or very nearly so, very much like the magnetic field of the Earth. For J0030 plus 0451, however, those jets are not aligned with the spin axis, not even close. In fact, there's 3 of them, and all 3 are in the southern hemisphere. There's one that is at the south pole of the star, but the other two are shaped like crescents and sit at about 60 degrees south latitude. So this pulsar, which is about 1,100 light years away in the constellation of Pisces, has been the subject of intense research. And the astronomers themselves haven't been able to figure out what has created the oddities in the magnetic field. Paul Hertz, the Astrophysics Division Director at NASA's headquarters in Washington, had the following to say. From its perch on the space station, NICER, the neutron star interior composition explorer, is revolutionizing our understanding of pulsars. Pulsars were discovered more than 50 years ago as beacons of stars that have collapsed into dense cores, behaving unlike anything we see on Earth, which seems to me to be a bit of an understatement. So we have a long way to go to understand fully how neutron stars work. But that's the way the universe is, you know? Every time you look out there, all you do is discover more mysteries. Fortunately, we have a tool that has over and over proved useful in answering these sorts of questions, the protocol we call the scientific method. It's also why I've always said that if you're interested in science, you'll never run out of things to learn. If you enjoyed this video, please give us a thumbs up. Our resources are down there, and please subscribe to our channel. Thank you.